Okay, let's start. So, yeah, we didn't even finish the first page of this chapter 5.1. Yeah, but yeah, before then, let me point out one thing related to the least square that we learned last time. Okay, so let's see. So one student asked about some question about this least squares. So yeah, so let's see. Okay, so in least square, we first consider the projection, orthogonal projection of B onto the column space of an A, right? So that was kind of initial starting point, right? But let's think about one special case where our matrix A and its column space spans the entire space. So for example, let's see. Suppose your column dimension of an A is just a 5, and you have maybe 5 or even more vectors. Yes, but at least, yeah, you guys know if you have 5 linearly independent vector, which is the minimum number to span the entire space R5, right? So 5 is the minimum number, but if you have 6 and then yeah, it should be linearly dependent, but yeah, if you can find at least 5 linearly independent vectors or columns in A, and then this whole A or column space of an A will entirely span our universe R5. In that case, so I wanted to ask this question. So if you pick up any B, so if you choose any B, and then that's already in the column space of an A, right? It's already in the column space of an A, and then what will be its orthogonal projection onto the column space of an A. So you start with the any particular B, but this B is already in the column space of an A, and what will be the projection of B onto the column space of an A? That will be just identical to just the original B, right? So I mean, it is a little bit tricky to think about the orthogonal projection in this case. I mean, at least in an intuitive sense, because our space is just a universe. So our point is somewhere inside of our universe, and so it's an orthogonal projection. I mean, we don't know where to project it to a certain kind of subspace, right? And so in that case, if you focus on the fact that the B is already inside of our column space of an A, and so in that case, this projection will be just the same as B. Okay. Okay. And then now, yeah, let's start with this chapter 5 about the eigenvalue and eigenvectors. And if you remember the property or the key aspect of this eigenvalue and eigenvector is, so given a particular matrix A, okay, and then you consider some special vector V, and that special vector is such that their matrix vector multiplication with the matrix A that will become just a simple scalar multiple of the original vector. Okay, and in this case, so again the situation is we are initially given A, and there exists some special vector V and this particular scalar multiple value, right? And then suppose you found, so in the case of an A equal to 1, 2, 3, 6, 4, 5, maybe 1, 1, 1. Yeah, let's think about this matrix. And then suppose 1, 2, 1, this vector was actually happened to be the same as maybe 5 times 1, 2, 1. Okay? And then suppose you found another vector given the same matrix. So suppose you found another vector that now satisfies maybe like this. Okay? So in this case, it's still converted into much easier form of scalar multiple of the original vector, which means for this special vectors, so in terms of their direction and the length of the vector, the direction will still be the same, but the length will only change even after multiplying the matrix A, right? So that was the key property of this eigenvector and eigenvalues. And here in this case, these scalar multiples can be different depending on your special vectors. So so far you found the two different special vectors, but their associated scalar multiple can be different. Okay, and then given the same matrix, like this same matrix, okay, you can in general you can find multiple such vectors satisfying that relationship, but each different vector may be associated with different scalar multiples. Okay, so that is the initial problem setting of eigenvalue and eigenvector. And this special vector is called eigenvector, and this value is called eigenvalue. And as you saw in this example, particular eigenvector and eigenvalue is paired. Okay, so you can think about one particular pair, and then the vector in the pair is such kind of special vector, and the scalar value is associated scalar multiple value. And then you can think about the pair as like this. Okay, this is an eigenvector and this is an eigenvalue, and another pair could be this, right? You have a different eigenvector and different eigenvalue. Okay, and then let me let me describe a little bit more about our problem setting. So first of all, let's think about the shape of the matrix A. So when when we talk about eigenvalue and eigenvector, we only consider the square matrix, not the rectangular matrix. And why? Why should that be? Why should that be so? So let's think about some rectangular matrix. Okay, rectangular matrix. For example, 4 by 3. In that case, suppose you have some special vector V, and then it should be represented as scalar multiple of the original vector V, right? And then does it even make sense? The answer is no. And now, why does it not make sense? Right. So after multiplying this, you will have 4-dimensional vector, right? So you cannot even think about the same vector dimension at all, right? So that's why we only consider the square matrix when talking about eigenvalue and eigenvector. So that is quite a basic but a really important part. And also, given a square matrix, and then so if it was a 3 by 3, and then our vector should be 3 by 3, and then we should have a scalar, right? And let's think about some special case. So here the question is it possible to have 0 vectors? So zeros. So the original vector that we considered as a special, so that had its own the length and the direction. But if it was a 0 vector, it doesn't even have any direction at all. So the key point of this eigenvalue and eigenvector is to preserve the direction of the vector, even after multiplying the matrix A. But the vector V, if it was just a 0 vector, and then it doesn't even have any direction at all. So we just exclude this trivial case, okay? So by definition, eigenvector, or this kind of special vector that we talk about, is it's only it's just a non-zero vector. We only consider the non-zero vectors as a kind of potential candidates for our eigenvector. Okay, so eigenvector should be non-zero vector. Okay, and then now let's think about another special case. Another special case is about this value, scalar multiple. So we have some non-zero vector here, and then can this scalar multiple be zero vector? Zero value as a scalar value. So here we consider the zero eigenvalue is valid or possible. Okay. So in that case, originally the vector had a direction, right? The vector had a direction, but if you multiply A with this non-zero vector, and then the resulting vector is still treated as the same vector, but the length became just a 0, right? Just a 0. So we can kind of say that, we can kind of safely say that the vector direction was preserved. At least the original vector has some direction, and then it just became as just a origin, or the 0 vector. And then a 0 vector can be considered as having any directions, right? It's a little bit tricky, but it's just a kind of conventional kind of a promise among the all the smart mathematicians. Okay, so we allow 0 eigenvalues. Okay, and let's think about this special case a little bit more. And then this question, or this equation, becomes this: A times B equals what? 0, right? More exactly, 0 times B, but it's still a 0 vector. And again, V should be non-zero vector, right? In order to be able to call that as eigenvector, right? And this question suddenly became quite familiar to us, right? So that is called a homogeneous linear system. And so if your matrix has non-trivial solution, and then that non-trivial solution, or that non-trivial vector, is one of your eigenvector, and then what is the corresponding eigenvalue? What is the corresponding eigenvalue? What is the corresponding scalar value in that case? Here in this case, what is the eigenvalue? 0, right? 0. So your non-trivial solution for a homogeneous linear system, that is your eigenvector, and the associated or corresponding eigenvalues are eigenvalue is 0. Okay. Okay, so let's see. Now we are ready to a little bit intuitively understand the definition of eigenvectors and eigenvalues. So eigenvector of a square matrix, right? N by n square matrix A is non-zero vector because we excluded the zero vector because that is considered to have no direction, and then I should satisfy this A times x, and we generally represent the eigenvalue as this lambda. Okay, so this guy is just nothing but the matrix A and the vector v, vector x, for example, and then lambda and x, the same vector x. Okay, and then if you found such kind of eigenvector and then associated scalar value lambda is called eigenvalue, right? Yeah, and then this non-zero vector has another name of this non-trivial solution, which just means non-zero vector, right? And then this non-trivial solution x, solution vector x, is satisfying this, and then this has the corresponding eigenvector as lambda. Okay. Okay. Then now let me show you one simple but really important trick to find out our eigenvector. So the exercise problem and also maybe some of your exam questions will be something like this. So I'll give you just one particular matrix, and then find out all these eigenvalue and vector pairs. So that will be one of your exercise question and possibly one of the exam questions. Okay. So in order to solve that problem, you have to start with this very simple but really important manipulation of this eigenvector value equation. So here I'm gonna move the right hand side to the left hand side as this. Okay, then I'm gonna change this guy. So if we think about it, a times x, and we have lambda minus x should be 0, right? So far so good, right? And then we change this guy with this value and then some big matrix and this. And this is lambda and x, right? And this is lambda and x. And then we can have identity matrix here, right? It's a quite simple trick, but it's a really important trick. And then now what we can do is to factorize these entire part as a. So this is an a and x, a minus I lambda I and x equals 0. So this guy again is, we have an a here and lambda and I. Okay, and then let's consider this part as matrix B, and Bx becomes 0, and then that suddenly became one form of homogeneous linear system, right? For a new matrix B, right? And that B is a minus lambda I, and this x vector is still our eigenvector, and that eigenvector should be non-zero vector, right? So we should find the non-zero vector here, which means this matrix B should have non-zero vector for its homogeneous linear system, and thus the columns of B should be what? The columns of B, or in order to have a non-trivial solution for this homogeneous linear system, and then we already know that your matrix should have like a free variable and linearly dependent columns and so on, right? So here the process is, so even though, yeah, so when thinking about this eigenvector and eigenvalue, and then they are paired, right? So they are paired. So we have to find this particular pair, both of these x vector and lambda or eigenvalue. But which one should we find first? Which one? Which one should we find first between eigenvector and eigenvalue? In practice, eigenvalue is the first thing that you have to find, okay? And that becomes like obvious in this process. And let me tell you why. So B is A minus lambda I. And suppose your matrix A, which is a square matrix, for example, it should be square matrix, right? And then, for example, it should be, it was a 3 by 3. And then it was, suppose it was having a invertible matrix or linearly independent column. And then A times X is equals 0. Does it have non-trivial solution if A was having a linearly independent column? No, right? But even if you started with this invertible matrix A, after you subtract lambda I from it, you should be able to have non-invertible matrix, because you have to find this eigenvector X as a non-trivial solution for this homogeneous linear system, right? So intuitively, this kind of process, in order to, so I mentioned that we have to find eigenvalue first. We have to first find the eigenvalue, right? And then by carefully changing your eigenvalue, you are making your matrix A singular or non-invertible, even though your matrix was originally invertible or having a linearly independent columns. By carefully changing lambda, you are making your matrix as having linearly dependent column, so that you can find non-trivial solution for this homogeneous linear system Bx. Okay, so this is a big picture of finding eigenvalue and eigenvector. How can we find the lambda? Yeah, so I will just I will describe it very soon. Okay, so let's think about first of all, let's think about the shape, or what is changing in the matrix A when subtracting lambda I from it. So it's very simple. So suppose you had 1, 2, 3, maybe 1, 0, minus 1, 1, 1, minus 1. Okay, and then we didn't talk about how we find the lambda yet, but let's think about the lambda as maybe 2, and you are subtracting out the identity matrix. Okay, and then what is the resulting matrix? Resulting matrix is 1 minus 2, right? And 0 minus 2 and minus 1 minus 2. And what about the off diagonal part? They will remain the same, right? So by subtracting lambda I from the original matrix A, we are subtracting the same value lambda along each of our diagonal entries, right? So that is the meaning of A minus lambda I. And then again, by doing this process, you are making your matrix as having linearly dependent column. Okay? Okay, then now, let's talk about how we can actually find such lambda to make a minus lambda I singular or non-invertible or having linearly dependent column. All of them are the same thing, right? So as you guys know. Okay, so in order to solve the lambda, we utilize the determinant, because a minus lambda I again should this homogeneous linear system should have non-trivial solution, at least one non-trivial solution, right? In order for this lambda to be your eigenvalue, right? Because in that case you should have non-zero eigenvector, right? And so in this case we can say that this guy is still a square matrix, right? Square matrix, and then this should be singular or non-invertible. In that case, from our IMT, and also using a determinant in the case of the singular matrix, then the determinant of it should be 0, right? And so again, even if your matrix A was invertible, so suppose your matrix A was invertible matrix, which was a good thing, right, in some sense, and the original determinant value of matrix A would have been some non-zero value, for example 5. In that case, it means your matrix A was invertible, right? But after subtracting lambda I from your matrix A, and then you now make your matrix A minus lambda I as having a 0 determinant. So that's how to make this matrix as non-invertible or having a linearly dependent column. Okay? And then this guy is so important equation. Oops. So this guy is a so important equation, and so that has a special name, and that is called characteristic polynomial or characteristic equation, and that is called a characteristic polynomial of your matrix A. Okay, so the reason for this name is because this equation is actually revealing some characteristic or some properties or some aspect of your matrix A. Okay, so that's why we call that as characteristic polynomial of an A, because it's revealing some characteristic about your given matrix A. And let's think about this characteristic polynomial in more detail. And this is actually a polynomial. So polynomial means, in Korean, what is it? polynomial 뭐죠? 한글로는 저걸 뭐라 그러죠? 네, polynomial. 네? 몰라요, 한글로? polynomial? 그렇죠. 다항식. So so this is actually a polynomial or 다항식, right? So what was a polynomial? Like 3x squared plus 5x minus 2. So this is a one kind of a polynomial, right? So it's composed of the summation of something like ax to the power of n, for example, and b no a n minus 1, x n minus 1, and so on, plus a 0 times x 0. So this is a general form of a polynomial. And here we have some known coefficients like 3, 5, minus 2. And then we of course have the variable, such as an x, right? And in this characteristic polynomial, what will be our variable? Our variable is lambda here. Lambda. Now let me give you one example. So let's think about this a simple 2 by 2 matrix, and this is your matrix A, and A minus lambda I. By just treating lambda as just a variable instead of just plugging a particular scalar value in, that will become 1 minus lambda and 4 minus lambda and 2 and 3, right? Okay, so this is your A minus lambda I, and let's think about its determinant of it, and it will become 1 minus lambda and 4 minus lambda, because in general this has the determinant formula, or determinant formula as AD minus BC, right? So we are multiplying all the diagonal elements, like 1 minus lambda, 4 minus lambda, and minus what? Minus 6, okay? And so here is lambda squared and minus 5 lambda minus 2. Okay, so after just writing all down, determinant of your matrix A minus lambda I, that involves lambda as a variable, and it became second order polynomial, which means the highest degree of your polynomial is 2. Okay? And then in general, if your matrix is a 3 by 3, and then your characteristic polynomial will become third order polynomial. And if it is 100 by 100, and then you will have a 100 order or 100 degree polynomial. Okay. And then let's see, we should set it as 0, and such lambda, the solution for lambda satisfying this equation will become your eigen value. Okay, and then why will we have nth order polynomial for our characteristic polynomial? Yeah, I mean, why is it true always? Why is it true all the time? So the question is, if we have like 100 by 100, then it is always true that A minus lambda and its determinant will be polynomial, but the highest degree will be like a lambda to the power of 100. Why should it be true? Why is it true? Yeah, so I'm not gonna give you the rigorous proof, but you can think about this kind of thought experiments. Like, so in this case, maybe it's like we can focus on some. Let's think about where we can find the lambda in our matrix. A minus lambda I. Of course, it's as we saw in this example. So if it was originally 3, and then 3 minus lambda, for example, and then minus 2 minus lambda, and 1 minus lambda, and 5 minus lambda, and then it means, the original diagonal value of matrix A was 3 minus 2 and 1 and 5, right? And then we don't know, So these off diagonal part doesn't involve lambda at all, right? Doesn't involve lambda at all. And then let's just give some value like 1, 2, 3, 4, 5, 4, 1, 0, minus 1, 1, minus 2, 1, 0. I just gave a random constant value. So in this case, if we think about the the determinant formula, and then we learned three different methods of computing the determinant of a particular matrix. Okay, and then the second one, okay, the second complicated one, second most complicated one among the three, that has been quite effective one, right? Which is about like a cofactor. So when utilizing the cofactor in order to compute the determinant, we typically select one column or one row that has the most number of zeros, right? So that's how we can save ourselves from like huge computations, right? And then this cofactor formula can be done by using particular row or column, but also it can be done by choosing those 4 values, right? Those 4 values. So yeah, it is just okay if we just select those 4 entries as a kind of starting vector, although that is not a vector, right? So what will be the sign corresponding to those values? For example, what is the sign? So if you remember some checkerboard pattern, so it's like, it's like a plus, minus, minus, plus, and minus, plus, and so on, right? And then those diagonal entries will have always what? Yeah, always positive sign, okay, plus sign, right? I mean, that's that. And then, so that was the sign. And then let's think about the remaining part in order to compute the determinant. So if we chose this guy, then we have to remove the corresponding column. So that is like a submatrix that we have to consider, right? And then it's like 3 minus lambda times determinant of this matrix, okay? This matrix, right? And then this part you keep applying this cofactor kind of a thing, and then let's just select this guy, and then we are ending up with this smaller one, and then this guy and this guy, and so this guy will have like minus 2 minus lambda, and determinant of, although we have some other terms, but let's see. Then this, this guy, okay, this guy is like this part, right? And then as you will see, because this 2 by 2 matrix we know is having a lambda squared, right? And then we have a lambda, another lambda here, and then another lambda here. That's that are multiplied together, and so we are having like a 4 lambda to the power of 4, okay? Okay, and then will it it have a more than fourth order term? So this is a little bit unorganized explanation, but let's think about this: a 4x4 matrix again, and then the same value, and then let's think about just a simpler case of picking up the first row, for example. And then this guy is the first case of choosing this first guy. And then let's move on to the second guy. Suppose we chose the second guy as this guy because we initially selected the first row in order to compute the determinant. And then the removed part is this row, right? And this row, right? This row. And then the remaining 3x3 matrix will be, it's a little bit messy, but we remove this this part and this part. So these and these, they are aggregated together to form 3x3 matrix, right? After corresponding columns and rows. In that case, even though the matrix is a 3x3, but we only have like two diagonal terms that have lambda, right? Because we removed this term that contained the lambda and this term that also contained the lambda. So the remaining terms that contains lambda is only 2, right? So in that case, the determinant of these parts will be just lambda to the power of lambda to the power of 2. So that will be your maximum degree. And this value that we initially chose, this doesn't have any lambda. Because we chose off diagonal entry, right? That didn't have the lambda, so that would have some scalar value, for example 3. And then the remaining 3x3 matrix will only have only 2 lambdas, and so the maximum degree or the polynomial order will be 2, right? So if we choose non-diagonal entry in our cofactor formula, and then the maximum order in this polynomial of lambda will be like n minus 2, or if it was 100 by 100, and then we will have definitely lambda to the power of 10, 100 when selecting all these diagonal ones. Then as we move onto the off diagonal ones, and then we will have 98 or less. Okay, it's you don't if you don't understand this specific part, and then it should be okay. But it's conceptual understanding, and that also reveals some interesting aspect or fact about your eigenvalues from your matrix. But it's out of scope. It's out of scope of our lecture. So okay, let me get back to this part where we consider this characteristic polynomial or characteristic equation when setting it as 0. Okay, and then let's see. Okay, if it is 4. Okay, then let me change it to okay, and then so it has some root or some solution, and then suppose this guy was having the solution of 1 or 4, for example. Okay, so I'm bad at creating a good example, but let's think about this guy. Okay, this guy has, so if we consider a minus lambda I, and then it is like 1 minus lambda and 2 minus lambda, and then I apply AD minus BC as a determinant formula, and then yeah, let's just do some math, and 3 lambda and plus 2, right, minus, so minus 28, is it right? And then it will become lambda minus 7 and lambda minus plus 4, right? And then the two solution for lambda is 7 and minus 4. And these two are your eigenvalue. Okay? Okay, and then how can we find eigenvector then? How can we find the eigenvector? So again, particular eigenvalue is paired with particular eigenvector, and different eigenvalue is paired with the different eigenvector. So we have to take care of each value of an eigenvalue, like a one by one. So let's think about this 7. Okay, let's first take care of 7. And then a minus lambda I will become like minus 6 and minus 5 and 6 and 5, right? And then if you remember the big picture about this process, and then by carefully choosing the lambda value, we are making this matrix as non-invertible, right? Is it a non-invertible? Or in other words, does it have linearly dependent columns? Are columns linearly dependent? The answer is yes, because these two columns are just having the same, exact opposite direction, which is all along the same line, right? So that's why these two columns are linearly dependent. So yeah, so magically we made our matrix A as linear as non-invertible matrix by subtracting lambda I, right? And then what was the next process in order to obtain the eigenvector? The next process is to actually find the non-trivial solution for this matrix times vector x equals 0, right? It's actually 0, 0, right? And then x is like x1, x2, right? And then what will be one solution for this x1 and x2? From here, these two will work as a linear combination coefficient associated with these two columns, the first and the second column. And then it's like if we set it as 1, and then if we set it as minus 1, and then that will make a times x become 0, because these second vector is just a scalar multiple of the first one with the minus 1 as a multiplier, right? So that's why we can just easily obtain this solution, right? Or you can of course do this row reduction, and then pivots and the free variables, and then you just move the free variables to the right, and then factor it out, right? And that's another way, or more formal way of obtaining that solution, right? But at least in this case, we can find this solution very easily. And then this 1 and minus 1 is 1 comma minus 1 is your eigenvector. So you now successfully found eigenvalue and eigenvector pair. Okay, this is how you find eigenvalue and eigenvector. And by using, we move on to minus 4. And then let's just use it. Let's just apply it from A. So 1 minus minus 4 will become 5, right, from here. And then 2 minus minus 4 will become 6, and 6, 5. Okay, So although this one looks almost similar, but this is a different matrix, and that is also having a linearly dependent column. So by using a different eigenvalue, you made your matrix A singular matrix or linearly dependent columns, right? And then it will have, so yeah, what would be the associated eigenvector for this case? So let's think about this intuitive process again. So the x is, so here if it was if it was 1, and then what would be the value here? Yeah. So I made a mistake here. So in this case, should it be 1 minus 1? Does it make a 0 vector? No, right? What should be the value in here? 1. Yeah. Sorry about the confusion. It should be 1, 1, right? So that will be the one linear combination coefficient that will make the linear combination of two columns as 0. Okay, then what will be this value? Here we have a minus 1 because these two vectors are the same, and then 1 times the first vector and then minus 1 times the second vector will become a 0 vector, right? So now this minus 4 is associated with this eigenvector, right? And then let's go back to, I mean, just to have an intuitive understanding again, or more concretely, what does it mean that we have this eigenvector, this eigenvalue, and this eigenvector? So your matrix A had, your matrix A was 1, 6, 5, 2, and your eigenvector was 1, 1, and then this guy will become 7 times 1, 1, right? Is it true? So you can evaluate it in order to verify that is true, right? And so if you use this special vector of 1, 1, and then your matrix A will not change the direction of 1, 1, this vector, but it will actually increase the length of the original vector by 7 times. Okay, 7 times. Okay. And then let me ask another question. So here, is it the only one solution? So in general, if you have a non-trivial solution in your homogeneous linear system, and then you generally consider it's a basis, but not the particular solution, which means, so if 1, 1 was one solution of your homogeneous linear system, and then what about minus 1, minus 1? Or what about 1 over 2, 1 over 2? So all these vectors are, satisfying this. They will work as the solution for a homogeneous linear system, right? So the direction was really important, and also if you remember, and then if you remember about the parametric vector form, we only considered the basis, right? The basis. And that was called a null space, and the null space, the basis of the null space was such kind of vector after we convert our general solution into a parametric vector form, right? So like factoring the free variables out, and then having the constant vector, like, and something like that, right? And so we thought about the number of basis vector, and then also the dimension of the null space, right? So the null, is the null space only having just a line or one-dimensional null space, or is it having like a plane as with the two basis vectors for your null space, right? Okay, so here the direction is only the direction matters when thinking about the eigenvector, right? Because the magnitude itself. So if you use this one, and then this one will be still satisfying 7 times the original vector, right? It is all, yeah, it is actually the same, right? So regardless of which vector you use, the original vector, I mean the direction will not change, and then the original length, the length of the original vector will be magnified or multiplied by 7 times, right? And so all these three vectors, eigenvectors are treated as the same vector, okay, as the same vector. Okay, and then let's think about since we talked about these dimension of the null space. So if we had a two free variable, okay, if we had a two free variable in your matrix A, which means so if we had a two free variable, and then what was the dimension of our null space? The null space will give you the two basis vector, right? And the null space is actually a plane, not a line, right? And then let's see. Yeah, so this is such an example of having two-dimensional null space. So suppose your matrix A is given as follows, and then since this is a first chapter, so it's giving you the eigenvalue already, but it's a simpler problem. But anyways, so the problem is already saying that 2 is one of your eigenvalue, and then we just subtract 2 from the diagonal element, and then this is your resulting matrix. That should be singular, or that should have a linearly independent columns, and then yeah, since it's like a 3x3 matrix, so let's just do the row reduction, and then what will we obtain? So it's like 1, minus 1, 6, and 0, 0, 0, and 0, 0, 0. Oh, sorry, 2. Okay, we just subtracted the first row. I mean, scalar multiple of the first row from the second and the third row in order to make all these values to be 0. But suddenly, those values became all 0, and then by using just one step, we already reached it, or already obtained echelon form, right? Not the reduced echelon form. And then here we can now see the pivots are only existing in the first variable, okay, x1, and then the second and the third one is just a free variable. So in that case, we have a 2 free parameter and also associated 2 basis vector, right? Yeah, so this is your parametric vector form, and these 2 vectors are the eigen vectors, right? And then they have the corresponding eigenvalue as what? 2, because we started with the eigenvalue of 2, and then we obtained these 2 different eigen vectors. Okay, and then just the null space of this a minus 2i. This guy has the null space like this plane spanned by the 2 basis vector as these, right? And then let's again think about this property. So if you choose this vector and then multiply a times 1, 2, 0, and then it should give 2 as an eigenvalue and 1, 2, 0, right? So that should be true. And also a times minus 3, 0, 1, and 2 minus 3, 0, 1. It should be also true. So you can easily verify it, right? Okay, and then what if we what if we selected one point, one vector from our null space, and then suppose this vector was, at least this vector should be able to, should be represented as a linear combination of those two basis vectors, right? And then suppose that linear combination was maybe 1 times 1 to 0 and minus 2 times minus 3, 0, 1. Okay, suppose this chosen vector was represented as a linear combination of our basis vector, because we chose this vector from our null space, right? Okay, so for this vector, what will be, so let's call this vector as, for example, y. Then what will be this? What will be the result of a times y? It is still 2 times y. 2 times y. And why? Why should it be that? Why should that be true? Okay, let's imagine the multiplication with the matrix A here. Okay, and A can be distributed to each term, right? And then A times this guy will change. I mean, this will be changed as like 2 times this, right? Because this was an eigenvector associated with the eigen value of 2. And then this guy is also changed the same vector with 2, right? Okay, and then we multiply this guy 1 times and minus 2 times, which were original linear combination coefficient. Okay, and then altogether, if we factor these two out, okay, and 2 times this part and this part will still be your vector y, right? So each base, because each basis vector is just stretched or multiplied for its length by 2, right? Its length became like 2 times larger or 2 times longer, but the direction is still the same, and so this linear combination vector y is also having the same direction, and also the length will become 2 times larger. Okay, so this point is described by these two figures. So initially you found maybe these two bases for your null space, and then after multiplying matrix A with this vector, and then this original vector will become 2 times larger with the same direction, and then this value will be also 2 times larger. But also for any other vectors, any other points, it will become like the same direction. We will have the same direction, and the length will become 2 times larger. Okay. Okay, and then I'll introduce another term. So again, we started from this eigenvalue of 2, right? And then it has its own null space for a minus lambda I, right? So if lambda was 2, a minus lambda I will have its own null space, and the null, any vector in your null space will satisfy this equation, right? So basically, your null space, any vector in your null space, is the set of all the vectors that satisfies this relationship. Okay, this relationship, and then this space is not exactly a null space of an A, right? It's exactly the null space of A minus 2I, right? And so this null space is this plane, and this subspace is called eigenspace. Eigenspace. So eigenspace associated with the eigenvalue of 2. Okay, so that has a special name of eigenspace, which is basically a subspace that contains all the vectors that satisfies this relationship with this particular eigenvalue. Okay, and then let's look at the first theorem. And this theorem is discussing about the special case where your matrix A is a triangular matrix. Suppose your matrix A was triangular matrix. And yeah, so before then, let me ask a kind of simpler question. Suppose your matrix A, so in general, we thought about the situation where your matrix A was invertible matrix. But what if your matrix A is already a singular matrix? In that case, the determinant of an A is already 0, right? So your matrix A already has a linearly dependent column. And then we can immediately say that about one of eigenvalues of this matrix. And what would be that eigenvalue? So the eigenvalue should satisfy this guy, right? And then by comparing these two, what can we say? One possible value for lambda. One possible value for lambda, 0, right? In that case, so again, we have to carefully choose the lambda value to make A minus lambda I is a non-invertible or singular, right? But if matrix A was already a singular matrix, and then we can just immediately choose the 0 value for your eigenvalue, right? In that case, what would be your eigenvector associated with this eigenvalue of 0? In that case, these are nothing but the null space, because in that case, we have to satisfy this solution for the eigenvector of an x associated with eigenvalue of 0. But since this part is 0, a times x should be 0, right? So just the non-trivial solution for homogeneous linear system, the original homogeneous linear system of Ax equals 0. And then that non-trivial solution is your eigenvectors, okay, associated with 0 eigenvalue, okay. And then let me ask one slightly different question. Kind of an opposite question. So if your matrix A is non-invertible, which means the determinant of an A is not 0. Okay? So in this case, so I'm just rewriting this equation again and again. And here, is it possible that lambda equals 0? Is it possible that lambda equals 0? So again, A is a singular matrix. A is an invertible matrix. And then, will it be possible that for some matrix A has a 0 eigenvalue? Is it ever possible? Is there any possible case, at least for just one case? So the question might be a little, I'm not sure if I described my question clearly, but my expected answer is actually no. So my point here is, if your matrix A, on the contrary from on the contrary to the previous case, if your matrix A is an invariable matrix, and then subtracting 0 times identity matrix, and then your matrix of this A minus lambda I will never be singular. Because in that case it will be the same as A, right? And then it's already saying it's not zero. So we can see some interesting property that if your matrix A is invariable and your matrix A will not have 0 as an eigenvalue. So it's always true. But if your matrix A is a singular, and then that matrix A will always have 0 as eigenvalue. Okay, so yeah, as you will see this in the next chapter, but so we had a long list of an IMT, invariable matrix theorem, and then all the different properties of that, right? When thinking about the square matrix, right? We had a long list, right? And then we can add another item, saying if your matrix A is a non-singular, and then 0 is not your eigenvalue. And on the contrary, your matrix is singular, and then 0 will be your eigenvalue. Okay. Okay, and then let me ask another related question on top of it. Let's think about this. Yeah, go back to this case of a singular matrix A. In that case, so we now know that 0 is eigenvalue, right? And then will it be possible that we have other eigenvalues other than 0? So is it possible to add non-zero eigenvalues as well, in addition to 0 eigenvalue? Will it be possible? What's that? Yeah, the first situation. So again, the situation is A is a singular matrix, and then we know 0, at least 0 is one of our eigenvalue. And then the question is, will 0 be unique eigenvalue, or will you be able to find other than 0 eigenvalues?
I think that lambda, any specific number of lambda, can return A to be invertible.
Can you say again?
If there is one specific lambda that makes
the matrix A
invertible, so I think we'll not be
yeah.
If there is any lambda can return back the A to be invertible.
So here the point is we have to make A non-invariable by subtracting lambda I, right?
Yeah, but it's already non-invertible.
It's already non-invariable. So the question is, can we find non-zero lambda that will still make A minus lambda I non-invariable? So it's like 1, 2, 2, 4, which is a right? And then let's start with the simple example of lambda and lambda squared minus what? 5 lambda plus 4 and minus 4. This is your characteristic equation, and we are removing it. Lambda squared minus 5 lambda and lambda times lambda minus 5, and so it is giving us lambda as 0 and 5, right? And so 0, which means without subtracting anything, so keeping A as it is already non-invariable, but you can find another lambda value, non-zero lambda value, to make A still non-invariable as a different matrix, as A minus 5I, right? Okay. So the time's up. So I will continue the next time.
with this again. I forget it
Oh,
from the
yeah.
high school. I don't know why.
So this is a so in the case of an A, B, C, D, and then the determinant of it,
AD minus
AD
BC.
minus BC, right? And so this guy is A minus lambda I because I just subtracted lambda along the diagonal, and then we have to compute the determinant, and
Yeah.
then this times this.
Yeah, at this time, this how you come to
1 minus lambda times 4 minus lambda
it be lambda squared and then minus 2.
minus 5 because it's as a simpler form it's like a lambda minus 1 and lambda minus 4,
yeah.
right? And so lambda squared and then minus 1 plus minus 4 which
Minus
is
5.
minus 5 lambda.
And then we square the
Yeah, we have a 4 here as a scalar, right? And then for BC term it will be 2 times 2, right? So that's why we have a minus 4, and so
yeah.
we have
Yeah, I
this.
understand the question. Yeah. Okay. Thank you very much.